Hello, am I audible?
Good
Yes,
evening,
ma'am.
madam. You're audible.
Yes, ma'am. You are audible. Good
Okay,
evening.
so good evening, everyone. Let's start our class. Sorry for the bit delay. The session actually got delayed by an hour. So today is the revision session for week 5 to 8. Okay, so we will cover these topics. So the topics are: first we will cover what is the exponential function and their properties are. Then one on to functions, composition of functions, logarithmic functions, sequences their limit, and then at the end we'll spend some time on limit continuity and differentiability of functions. Okay, so these are the topics that we are going to cover. What I'll do, I'll first take the basic definition of each and every topic, and after that we will take some examples, 1 or 2 examples related to that topic. So in this pattern, we'll proceed through each and every topic. Okay. So that's the plan for today's class. In between, if you guys have any doubts, you can either unmute yourself and ask, or you can just type in the chat box. I'm looking at the chat box. Okay. Is there anything you guys want to tell?
Man, just wonder.
For all of my fellow students, until madam completes all the topics which has been listed, apart from this, any other questions you ask, we can ask in the last.
Yeah, that will be better so that it won't disturb the flow of teaching. Okay, so don't worry, we can take this session at, if the time don't permit, we can extend it by half an hour or 1 hour. Okay, so don't worry about that. Okay, so let's start with the exponential function. In between, if you feel that there is anything lag or something from my side, just let me know by unmuting yourself. Okay. So exponential functions. What is an exponential function? So what we want to define a function which has this type of form, that f of x is equals to a to the power x. Okay. So here what we want that for each x, the output should be a to the power x. Where what is this a? A is our the base of the function, and it is already fixed. So first what we'll do, we'll fix some number, some real number. And what are the properties of a? So a is any real numbers. You can take any real number, but the thing is, a is not equals to a should be strictly greater than 0, and a is not equal to 1. Okay, so that means a is not equals to 1 and a should be strictly greater than 0. So you can say that any real number with these two properties, that a should be strictly greater than 1, a should not be equal to 1 and a is strictly greater than 0. The reason behind that is, if you take a is equals to 1, then this is nothing but a constant function, right? Because we know that 1 to the power is nothing but 1. So if you take 1, a is equals to 1, it will change into a constant function. And if you take any negative number, so for example -1, then we know that -1 to the power 1 by 2, that is square root of -1, is not a real number, right? So what we want this function to be defined from all real number to real number, right? So we want the domain of this function to be whole real number. So that's why we are avoiding a to be any negative number, -1, -2, or any negative number. Okay, so that we can get a well-defined output. That's the only reason for these two conditions. Okay, so now we are defining a function f from R to R whose expression is f of x is equals to a to the power x, right? So that means the outputs will be a to the power x type. You can take any example. So for example, if you take f of x is equals to 2 to the power x, then this is an example of exponential function. Okay, so now I'll explain the properties of exponential function by its graph. So I'll take two cases. So the first case is when the value of a is between 0 to 1. Okay, so obviously we are not taking 1, so that's why I'm dividing into two cases: when the value of a is between 0 to 1 and when the value of a is strictly greater than 1. So when in this case, when the value of a is between 0 to 1, this exponential function's graph is nothing but like this one. Okay, so it's a decreasing graph which intersect at a point, so we can find out the y-intercept. So we know that if you put the value of x to be equal to 0, a to the power 0 is nothing but 1, right? So that means when x is 0, the value of y is 1. So the y-intercept of this function e to the power x is 0, 1. And it is approaching towards x-axis. Okay, so it is not touching x-axis, it is approaching toward x-axis. So for this one, for this particular case, you can take the example of the function f of x is equals to 1 by 2 to the power x. Okay, so here you know that as you proceed the power of x, so this is what? This is 1 by 2 to the power x. Correct? So as you take the much larger values for x, the quotient will become, the denominator will become bigger. So the whole value will become a little smaller, will be very smaller, right? So that's why this function is approaching toward x-axis, but it never touches x-axis, because the reason we cannot find any x for which this whole thing will become 0, right? So this is the thing for this particular case. So now for this case, let's discuss some of the properties. So we know we'll take care of on1 and onto function later. So we can talk about the end behavior of this function and the nature of this function, right? First thing is, in this case, this function is a decreasing function, right? So first thing is, it is decreasing. It's kind of obvious by just looking at the graph, because as we the values of x are uh, tending toward infinity, the value of function is decreasing, right? So it's a decreasing function. Now you guys can tell me the limits here. So what will be the limit of limit extending to infinity, a to the power x in this case?
It will be 0.
0, correct? It is approaching towards 0, but it never gets 0. So the limit is 0. Now the next limit, the other end. So the limit x going to minus infinity, a to the power x. What will be this limit now? As x is going towards minus infinity, where is function approaching?
Plus infinity.
Plus infinity, right? So here end behavior is kind of obvious. As x is going to infinity, the function is reaching toward x-axis. That means reaching to 0. And as x goes to minus infinity, the function goes to infinity. Okay, so this is the end behavior of function, and this is the graph of function. Okay. Now let's discuss the second case, when the value of a is strictly greater than 1. So in this case, the function actually behaves a little different from this one. So it's an increasing type of function in this case, when a to the power x. Okay, and then what will be the y-intercept here? So we will take the value of x to be 0. When x is 0, a to the power x will become 1. So y-intercept is same. But in this case, what is happening? The function is an increasing function. We can easily see just by looking at the graph. Okay, and now same thing. So in this case, the function will be increasing. Right. What will be the end behavior? That limit extending to infinity, e to the power x. What will be this limit?
Infinity.
Correct. It is infinity, because as x goes to infinity, the function is growing towards infinity. And what will be this limit? Limit x going to minus infinity, e to the power x.
0.
0.
Right. So this is 0. This limit is 0 and another limit is infinity. Okay, so this is the exponential function. So there are other properties of exponential function, that is 1 1 and onto. So first what we'll do, we'll discuss what is 1 1 function, onto function. What are the ways by which we can check a function is 1 1 or not, or onto or not, and then we'll go to
Ma'am,
yeah.
second graph is for a power minus x.
No, this is for a power x, but when the values of a is strictly greater than 1. For example, 2 to the power x or 3 to the power x, and so on. So generally it looked like this. Okay. Is that
And
okay?
first one is less than 1. A
Yeah.
is negative.
When a is between 0 to 1, not negative. Okay,
Now,
because for negative it is not defined.
one interesting question, madam. This one,
Yeah.
a power x, you have given the second. Madam, she asked whether it is a power minus x. What will be the graph of a power minus x?
So what happened whenever we try to find out, it will just reflect. So it will be the graph of this one.
Along y-axis.
Yeah, we will reflect that along the y-axis. If you change x to minus x, the graph will be reflectable about the y-axis.
Okay, so where is the question of 0 to a to, I mean, 0 less than a less than 1 and a greater than 1? So minus x means, okay, 1 by x. Okay.
Yeah, so you can e to the power minus x is 1 by e to the power x. This thing we can do, right? No.
Okay, okay.
Yeah, correct. Yeah.
But minus x, when we are giving x-axis, for example, a power minus x, and a is greater than 1,
Hmm.
that is how we are, for this particular thing, if you see, is when you put minus x, what will be the y coordinate, I mean y value?
See, a to the power minus x, this can be written as a to the power x to the power minus 1, right? Which is 1 by a to the power x, right? So
Okay.
here you can say that this is same as 1 by a to the whole power x. Okay. Now, if here you are taking a strictly greater than 1, then 1 by a will become strictly less than 1, right? So now this you can say that this is a some b to the power x. So this will change into the first case.
Okay.
Okay.
Okay, madam. Okay.
Like this computation we can do. Or else you can say that, okay, since we are replacing x by minus x, the graph is just reflected about the x-axis.
Y-axis.
Sorry, y-axis.
Okay. Okay, ma'am. Thank you.
Okay, now let's go to the next topic, which is 1-1 functions. So what are these 1-1 functions? So 1-1 is just a property of a function. So suppose we have a function, then when we will say that a function is 1-1. So this 1-1 means for a one input we are getting one output. So that means here for each and every output there is associated a single input. So what does that mean? So we say f is 1-1, f is 1-1. If you will take two different inputs, so that means suppose x1 and x2 are two different input, x1 is not equals to x2, and then if you compute the output related to these inputs, that is the output means f of x1 and the f of x2, that is the values of f of x1 and f of x2, these two values should be different. Okay, so that means for different input we should get a different output. So if a function satisfies this property, then that function is known to be 1-1 function. Okay, so that means for two distinct inputs we are getting for two distinct inputs x1 and x2, we are getting two distinct output, f of x1 and f of x2. Okay, so this is known to be a 1-1 function. Now how can we check a function is 1-1 or not? So first thing is we can just check by the definition. So this is the first way. You can check the statement. If you get two different inputs for which the output is same, then you can say that this function is not 1-1 function because it is contradicting our definition. Okay, so one simple example we can take. Suppose we have a function f of x is equals to x square. Okay, so here I can take two different inputs, namely x1 to be 1 and x2 to be minus 1. Right, so here it is kind of clear that x1 is not equals to x2, but if you compute the values of f of x1, so f of x1 is 1 square, which is 1, and f of x2, which is minus 1 the whole square, that's also equal to 1. So that means here x1 is not equals to x2, but what we are getting f of x1 is equals to f of x2. Okay, so this is contradicting our definition that there exist two different inputs for which we are getting the same output. So now this will implies that f of x is equals to x square is not a 1-1 function. Okay, so that's how you can find out that a function is 1-1 or not by checking this statement. Okay, so this is a statement, right? So it contains two parts. One is the if part and another one is the result. So what you have to do, you have to assume the if part and then prove the result if you want to say that that particular function is a 1-1 function. Okay, so for example, I'll take another simple example. Okay, so suppose someone asks you that f of x is equals to 3x plus 2. Is this a 1-1 function or not? Okay, so it seems like, okay, this is the equation of line, so it may be 1-1. But can we prove it that it is a 1-1 function or not? So for that, what you have to do, you have to prove the statement. Okay, so whenever in mathematics there is a statement which you have to prove, what you will do, you will assume the if part and using the if part, trying to convert the result. Okay, trying to get the result using some steps. Okay, so same thing we will do here. What I'll do, I'll say, let us assume we have two different input, x1 not equals to x2. Okay, so this is our assuming part, if part, right? I'll upload these notes over the calendar, so you can go and then download it from there. Okay, so suppose I have assumed the if part, that is x1 is not equals to x2. So if x1 not equals to x2, then we know that 3 multiple of x1 is also not equals to 3 multiple of x2, right? Because if you have two real numbers, then any constant multiplication of these two real numbers will be different if the real numbers are different, right? Similarly, you can say that, okay, this 3x1 plus 2 is also not equals to 3x2 plus 2, right? But what is this 3x1? So if you compute the value of f of x1, this is nothing but 3x1 plus 2. So this is your f of x1. Now what is this 3x2 plus 2? This is your f of x2. This is 3x2 plus 2. So f of x1 is not equals to f of x2. So here you have proved the statement which says that if this statement is true, then a function is 1, 1. So it means that f is 1, 1 function. Okay. Is that clear? How to prove a function is 1, 1 or not? If you sense that a function, this function might not be 1, 1, so then what you have to do, you have to find out such two numbers. For those numbers, we are getting different outputs. Okay. And if you feel that, okay, this function can be a 1, 1 function, then you have to go like this. You have to assume x1 not equals to x2, and then try to prove f of x1 is not equals to f of x2. Okay. So these are the ways. Now another simple way is using a horizontal line test. Okay. Is that okay? Any doubt so far?
Madam, if f of x1 is equal to f of x2, then
Mhm.
it is not 1, 1, right?
Yeah, it is not. If f of x1 is equals to f of x2, then it's not a 1, 1 function.
Ma'am,
Yes, Nari.
my assumption was wrong. So I started doing x1 not equal to x2, the procedure what you have done. But my function is f square. I mean, f of x equal to x to the power of 2. So in the how I would continue actually, because 3 x1 square is not equal to x2 square, it will come. Then we have to take a root.
Yeah. Then for root taking, we have two parts, plus and minus.
Plus or minus.
So, so there it become.
Then
there you have choices, right?
Okay, f of x1 will become, I mean, okay. So once I get two roots means, then I can understand that this is not 1, 1, because for one input, there can be only one output. But for
Correct,
the other, if it is two roots are there means, for one input, there are two outputs.
Yeah. No. Not for two outputs. For two different inputs, we are getting same
Inputs
output.
one, yeah, same output.
Same output. Okay. Now the next test is horizontal line. Yes, sir.
Ma'am, I have actually read somewhere that we can actually take the contradiction of this and prove it, ma'am.
Yeah, that's
Like-
also correct. So, for example, you can check this statement too. That assume that f of x1 is equals to f of x2, and then try to prove x1 is equals to x2. So you can also take the negation of this one to prove the 1, 1 function. So these two definitions are equivalent. The x1 not equals to x2 implying f of x1 not equals to f of x2. This definition and these two definitions, they are the same, because what is the first statement? It's just the negation of the last one, right? So both are just the negation of each other. So both are same. Actually, both statements are saying the same thing. Either for the same output, you are getting same input, or for two distinct input, you are getting two distinct outputs. Okay. So this thing also you can do. Is that fine? Any doubt? Okay. Now the very well-known test is horizontal line test. So in horizontal line test, what you will do? So suppose a graph of a function is given to you. Some graph of a function is given to you. Now what you will do? You will draw several horizontal lines. Draw several horizontal lines. Okay, so you'll draw several horizontal lines, and if there exists one line which is intersecting the graph of a function more than 1 points, then we can say that that function's graph or that particular function is not a 1, 1 function. Okay, so you'll draw several horizontal line, and if there is an horizontal line, which intersect or cut the graph more than once, then that is not a 1, 1 function. Okay, so this is known to be horizontal line test. So if you have a graph of a function, what you will do, you'll just draw several horizontal lines, and then if there is a horizontal line which is intersecting the graph more than once, then it will show us that what is actually happening here. So this is one input x1 and this is another input x2. So since this particular horizontal line, so suppose this value of y is some 1. Okay. So here what is happening? The function is taking at f of x1, the value of function is also 1. And at f of x2 is also the value of function is 1. So if a horizontal line intersected 2 points of the graph, it means that for 2 distinct input, you are getting the same output, which is contradict the definition of one function. So that's why this horizontal line test says if you draw several horizontal lines, several means you have to draw so many horizontal lines. And if there exists one line which is intersecting the graph more than once, then it will tell you that that function is not a one function. Okay, is that clear? Any doubt in this horizontal line test?
Ma'am, suppose if we take a parallel line like y equal to 1,
Hmm.
is that 1 to 1?
Parallel line, okay, so you are asking if you take this function, f of x is equals to 1, right? It is the
Yeah.
line y is equals to 1. Now, this is not a one
Yes.
function, right? Because f of 2
Yeah.
is 1, right? F of 3 is 1.
For multiple values, same output it is given. So
Yeah,
it is not.
not a one function, right?
Got it. Got it. No, got it. Thank you.
Okay. So this is horizontal line test. So these are the three ways by which either you can say that, okay, since this is failing, the function is not 1. So one is this particular statement. Either you can prove the statement or you can use it as a contradiction to say that for the same output, I am getting two different inputs. So it's not a one function, or you can use the second one. And another one is this horizontal line test. So you can use any of these three to show that, or to say that this function is 1 or not. Okay. Now there is another type of function which is onto function. And these 1 function they have another name which is known to be injective functions also. Right? So this is 1 function, or they are also known to be 1-1 also. So 1-1 is also same. 1-1 functions or injective functions. So these three functions are same. Okay, these are just name given to the same property. Injective function, 1-1 function, or 1-1 function. Okay. Now the second type of function is surjective function or onto function. Onto functions are known to be surjective function. Okay. So what is a surjective function? So suppose you have a function f from a set A to B. Okay. Now this function is known to be surjective function if for all values of B, for all B belongs to B, there is some A, there is at least an A belongs to A, such that this f is taking this A and mapping it to B. So that means for every element of B, we need a pre-image, right? On which if you apply the function, we'll get that element back. Okay, so this is known to be onto function. So if this is happening, then we are say that this is an onto function. There is one more notation of onto function. We know that what is a range is, right? So what is the range of a function? Range of f. So if you have a function f from A to B, then what is range? So range is nothing but you have to select all those elements from your codomain which actually has a pre-image, right? So all those B belongs to B. Such a way, there is an A belongs to A such that f is mapping this A to B. Okay, so this is known to be range of f. So what are onto functions? So for onto function, the range is same as the codomain. Range of f is same as the codomain of f. Okay, those functions are known to be onto function. Okay, so what are the onto functions? So first thing is the range set should be equal to the codomain set. That's all. That's all you have to remember. If you understand the range, what is range? So range is those values from your codomain which has pre-image, and if all values of codomain having pre-image, then that function is our onto function. Okay, is that clear? The definition of onto function? Any doubt? I'll take
Just one doubt. Ma'am. So,
yes.
codomain, in all the cases, the codomain will be the set of real numbers or not?
Until and unless specified. So if they specify you that this is your codomain, then you have to consider that. And if they haven't specified, then it's just a real number. Okay. Until and unless the question specified then you can consider the whole real number as your codomain. Okay. So now for finding onto this, only thing you need to check is the range of f should be equal to codomain of f. But how you can check the ontoness? By the graph. By the graph. Okay. So by the graph, how can you check? So by the graph, what you have to do? Suppose this is the graph of a function. So you have to check the end behavior of the graph. So if as x goes to infinity, this f of x either goes to infinity or minus infinity, this thing, or so that means what you have to choose, you have to check the limit. So if limit x goes to infinity, f of x is infinity, or limit x goes to infinity, f of x is minus infinity, plus with this. So you need any one of these situations. So either x goes to infinity as x goes to, sorry, either f of x goes to infinity as x goes to infinity, or f of x goes to minus infinity as x goes to infinity. Okay, any of among these two cases, you need at least one, plus with, that means one more limit we need, and that is same as like this one. So limit x goes to infinity, f of x is equals to minus infinity, infinity, or limit x goes to minus infinity, f of x is equals to infinity. Okay, so what I can do, I can give you the proper cases. So ultimately what I mean either either limit x goes to infinity, f of x is equals to infinity, and limit x goes to minus infinity, f of x is minus infinity. Either this one, this statement, or the converse of that. That means as x goes to infinity, your function is going to minus infinity from this side, and as x goes to minus infinity, the function values are going to infinity. Okay, so by graph what I mean, so there are two cases. So one thing is either this one as f of x goes to infinity as x goes to minus infinity, plus this situation. Okay, so one is this situation you need, or the other situation will be this type of situation. Okay, so among these two situations, if you have any one of them, you can say that that function is a 1-1 function. So if we have any one case, if we have any one of them, then it is a 1-1 function. Okay, is that fine? So by graph, you have to check the end behavior of a function. So if you are getting that, okay, from this one f of x is going to infinity, from this one f of x is equals to going to minus infinity, then you can say it is 1-1 or this particular. Okay, so here what is
1-1 or onto?
Sorry, onto function. In my mind, it's onto it. Sorry, thank you. So it's a onto function. Okay, so ultimately what is happening here, so suppose I'll take the first case where function is growing to infinity from this one and growing to minus infinity from as it goes to minus infinity. So here what happen, if you take any value of y, and I'm assuming that codomain is the whole real number. Okay, so here if you take any value of y, then that value will intersect the graph at least once, right? Then that particular line, suppose this is y is equals to -2, then that particular line obviously will always intersect the graph at least at one point. So that is what is happening here. At this particular value, suppose x is equals to -5, so f of -5 is equals to -2. So that means for -2 we are getting some pre-image. So that's the idea. So if a line intersect the graph, means for that value of y we have a pre-image. And ultimately if we have such type of situation, then we know that obviously any value of any horizontal line will intersect the graph. Okay, so we can also say the thing this thing using the horizontal line, similar to the horizontal line test. What we are saying, so if all horizontal lines, all right, if all and in the case of the function is being from real number to real number. Okay, so if all horizontal lines intersect the graph at least once, then we can say f is onto. Okay, so if all horizontal line is intersecting the graph of function at least once, then we can say that f is an onto function. Okay, so this, you can remember the statement similar to the horizontal line test. So in 1-1, what we need the one line should intersect the graph at one point, not more than 1 point. And here what we want that every line should intersect the graph at least once. Okay, so then we can say that for that value of y, we have some pre-image. But although for checking onto-ness is not that easy as compared to 1-1. For 1-1, we have very precise 3 ways. So among these 3 ways, we always work. But for onto, checking this one or checking the range is also not that easy. Okay. Any doubt?
Ma'am, can you repeat the statement again?
Yeah. So actually what is happening here, we want all horizontal lines to intersect the graph at least once. At least once means at least there should be 1 point.
Not this one, ma'am. The before one.
The 1-1.
No, ma'am. The onto statement before you gave this, before this, this one, ma'am. This one, ma'am.
This limit one.
Yes, ma'am. Yes, ma'am.
So here what is happening, if you have such type of situation, then obviously there will be a suppose the function is growing to infinity from this side and growing towards minus infinity from this side, right? So then obviously there will be one line, for any line, for any horizontal line, there will obviously some part of x which will intersect the line, right? Because you have to go to infinity and you have to go to minus infinity. So you'll take any line that will obviously intersect the graph at least once, right? So it ultimately say that for that value of y, we are having a pre-image. Are you getting my point?
Yes, ma'am.
Okay, you can think about, so let's take one example. So suppose I'll take the example of f of x is equals to x cube. Okay, so what is the graph of f of x is equals to x cube? So the graph is very simple, something like this. Okay, so here what is happening, as x going to infinity, this is going to infinity, and x goes to minus infinity, this is going to minus infinity. Right. Now you want to check that this function is onto or not. So by the limiting criteria, we can say that, okay, by the limit one, that limit statement, I can say that this is okay. This is fine. This is an onto function. But how we can actually see? So see, what we need for every real number, there should exist a pre-image. So what you'll do, you'll take any value of y. Y is our codomain value, right? F is a function from real number to real. So what you need to do, you have to find a pre-image for y. So what you'll do, you'll just draw a line here, and whatever the point you will get, that will be your pre-image, right? So that means for this, suppose this is some x is equals to 3 and this is y is equals to 9. So at x is equals to 3, the value of y is 9. So that means this 9 is having a pre-image. So you can take care of any value of y. If you draw any line and whatever point you will get, that is the point of x comma f of x. So that means for this output, I have this particular input. That's the meaning of cutting the graph. Okay. So if this line cuts intersect the graph, for that output, I have an input. For example, here I'll take any random value y0. Okay. So for this y0, what will be your input? Your input will be here. So this is your y0 and this is your some f x0. So this y0 will give us f of x0. Okay, because this point is lying over the line and the graph both, right? So it should satisfy the graph also and the line also. So the graph works with the expression f of x, and the line works with the expression y is equals to y. So y is equals to f of x should be equal to y is equals to y naught. So f of x naught should be equal to y. Okay. Are you getting the essence?
Yes, ma'am.
Okay. Any doubt?
Ma'am, for every horizontal line, it should cut the function, right?
Yeah.
Okay.
Every horizontal line. Okay. So this is the horizontal. I mean, these are the two ways for checking onto. One is this one, range should be equal to codomain. And if you want to go by the graph, you have to take care of either the limits, you can remember the limits, or you can check like this, that every horizontal line should intersect the graph at least once. Okay. So these are the 1, 1 and onto function. Now let's get back to, so there is one more functions which are bijective functions. So bijective functions are those functions which are 1, 1 as well as onto. Okay, those are the bijective functions. So if you have both properties, then that function is a bijective function. Now what happened? For every bijective function, we can define the inverse of a function. So what is the inverse of a function? So if you have a function f from a to b, you can define another function f inverse, which will be a function from b to a. So that means here the role of codomain and range will interchange. So if we have a function f from a to b, which is 1, 1 and on to both, then we can find a function f inverse from b to a, which is also 1, 1 and both, 1, 1 and on to both, with such that if you compose, as we look into composition function, so if you compute f composition of f, or if you compute f composition f inverse of x, you will get x back. Okay, so such a function is known to be inverse of a function. Okay, so we are just defining another function for which the domain and codomain is changed. So we are discussing from week 5 to 8. Okay, so though that function is the inverse of a function. For example, you can simply take, suppose f of x is equals to x cube we have as like the before. So by the graph also, by the horizontal test also, you can say that f of this is 1, 1 and on to both. Right? So f of x is equals to x cube is a 1, 1 and on to function. So for f of x is equals to x cube, I can define f inverse of x to be under the root of, cube root of x. Right? Now this will work as a inverse of this particular function. So the meaning is, for a function which is 1, 1 and on to both, for such functions, we can define the inverse of a function. Right? And that invertible function, if f is from a to b, then that function will be from b to a. So let's talk about the exponential function e to the power x. So suppose I have the function f of x is equals to e to the power x in both cases, when a is between 0 to 1 and when a is between strictly greater than 1. Okay, so by the graph, what we can say, and suppose f is a function from real number to real. Okay, so this is the graph for this one, and this is the graph for this one. Now, what you can say, is this 1, 1 or not?
Yes, this is 1, 1, right?
This is 1, 1, right? Because no matter what horizontal line you will draw, it will intersect the graph exactly at 1 point, not more than 1. Right? So yes, it is a 1, 1 function. So it is 1, 1 function. What about this one, this case, when a is strictly greater than 1? Same thing, right? Any horizontal line will intersect the graph obviously exactly at 1 point. So it is also a 1, 1 function. So 1, 1 is yes. What about onto? Is it onto this case?
No.
No, ma'am.
No, right? Because why? We are taking codomain as the real number. So if you take the value of y to be equal to -1, then there is no x which can consider as an output and give us -1 as an which can consider as an input and give us -1 as an output. Right? So for this y is equals to -1, I don't have any pre-image. So that's why this is not onto. If you take codomain to be real number. Okay, what about this case? When a is greater than 1?
No, ma'am.
Same thing, right? We can work with y is equals to -1. For this value, I don't have a pre-image. Okay. Now, here we discuss 1, 1 and onto both. So what is the problem here we having? We are having that the function is not becoming onto. Okay, in both cases, but it is 1, 1. So what we can do, we can shrink our domain to define a new type of function, which will be 1, 1 and onto both. So for example, if in place of real number to real number, if I say that f is a function from real number to open interval 0 to infinity, with the expression f of x is equals to a to the power x. Okay, then this will be 1, 1, obviously, because the graph will be same. What about onto? So we can also say that this will be onto as well, right? Because what will be the range here? So in this case, what will be the range of function? Range of f is open interval 0 to infinity. Because if open interval 0 to infinity, for any value, we can have a pre-image. Correct? So here we are taking range as a codomain for the function. That's why it's becoming onto. Okay, is this fact clear to everyone?
Yes,
Yes, ma'am.
So that
Ma'am,
means
in the
Yeah.
previous case, how codomain and range both are same?
no, in this case it's not same. because range is open interval 0 to infinity and this is real number, so that's why it's not a onto function. Okay, but if we shrink our
Ma'am,
codomain,
it is already given. That's
yeah, it is already given.
yes, ma'am. Okay.
Okay, and here if I say that I have a function from real number to open interval 0 to infinity with the expression f of x is equals to a to the power x. Now here it is range is same as codomain because the range of f is open interval 0 to infinity and this is same as your codomain. So here it will become an onto function, right? So that means now we have a 1 1 and onto both properties, so we can define the inverse of this function. So whatever inverse of this function is, that function is known to be the logarithmic function. So we'll define a function log. So we know that if f is a function from a to b, its inverse will be a function from b to a, right? So I want to define the inverse of this function, and this function is from real number to open interval 0 to infinity. So the inverse of this function, which I'm saying that it's a log function, this will be a function from 0 to 0 infinity to the real number. So that means here the domain of log base a. So as we specify the qualities of a here, so a is not equals to 1 and a is strictly greater than 0. Both things will stay in the log also. So that means here the base a is strictly greater than 0 and it's not equal to 1. Okay, so I am defining the inverse of this function a to the power x with shrinking the codomain 0 to infinity. So now it will become 1 1 and onto both. So I can define the inverse, and that inverse I am saying it is denoted by log base a. And the properties of a are a could be any fixed real number. First we'll fix a and then we'll talk about log. Okay. So in both cases, first we'll fix some value of a and then we'll talk about the function. Okay. So here the value of a could be taken as any positive number or not equals to 1. Okay. And how this log is defining? So the log base a of x is equals to y if and only if. So see here we want inverse function, right? So we have to take x as, if you want to take x as an input and giving y as an output, the inverse function will change. So that means a to the power y should be equal to x. Okay. So in this way, using this particular line, we are defining log function. So we'll say log base a of x is equals to y if and only if a to the power y is becoming x. And the reason behind this is we want to define the inverse of exponential function. Okay, so that's why we say log is the inverse of exponential function. This is the definition of log. Okay, so this is the definition. That's how we are defining it. There are several definitions. So you can define log function in various way. You can also use integration. You can also use series and those things. But this is the simplest one. Simplest one, since we have exponential function. So I'll repeat the story. Story is we have an exponential function. That function is originally not onto if you consider the real number as your codomain. But if we shrink our codomain to 0 to infinity, it will become onto, and it is 1 1 and onto both. So that's why it's a bijective function. And that's why we can define an inverse. So for inverse, I'm saying that a log base a, another type of function, which is from open interval 0 to infinity to real number, is the inverse of this function. We can define it as log base a of x is equals to y if and only if a to the power y is equals to x. Okay. So for example, you guys know that log base 2 of 4, this is equal to 2, right? Because we know that 2 square is equals to 4, right? So same things. So if 2 is confusing, we can take 3. So this is 8, 3. So 2 to the power 3 is equals to 8. Okay. So this is log base a of x is equals to y if and only if a to the power y is equals to x. Okay. That's the definition of log function. Is that clear? Any doubt so far?
No, ma'am.
So now one more remark I want to give. So if you have the graph of f, if you have the graph of f, then graph of its inverse, graph of f inverse is just a mirror image. Mirror image of graph of f about the line y is equals to x. So that means if you have graph of f and if you want to find out graph of its inverse, then it's nothing but the mirror image of graph of that function about the line y is equals to x. Okay, so what you'll do, you'll put a mirror over the line y is equals to x, and then find out the mirror image. That will be your inverse of that function. Okay, so we'll do the same thing to find out the graph of log x. So what I'll do, we initially have the graph of y is equals to x. Y is equals to, suppose I'll take one specific value of a 2 to the power x. And I want to find out the graph of y is equals to the log base 2 of x, right? So what will be that? That will be your mirror image about the line y is equals to x. So let me share my screen. Okay, so here you can see in the screen that this is the line, this green one is the line of y is equals to x, this y is equals to x. Initially we have the graph of 2 to the power x, which is the red one.
Ma'am,
Yeah.
screen is not visible.
My screen is not visible to everyone. Anyone?
It's visible.
It is
Yeah,
visible.
it is visible. With another account, okay? This MA11 account. Okay, so here this one is the line y is equals to x, the green one, and we want to find the inverse graph of inverse of this red one. So what we'll do, we'll place a mirror over the green line and find the mirror image, and that mirror image is the red, this blue one. So that means if you have the function 2 to the power x, the graph of log base 2 of x will look like this blue one. And this is true for any a which is strictly greater than 1. Now here in place of 2 to the power x, if I want to find out the graph of 1 by 2, then what I'll do? So suppose I want to find it by 1 by 2. So this is the graph of 1 by 2 to the power x. And here the base will change into 1 by 2. Right. So now this blue one is the graph for all values of a which are strictly less than 1. Okay. So I'll give you the general graph, but this is how we are we can compute the graph of inverse function just by taking the mirror image. So here suppose you have placed a mirror over this green line, then this part will have the mirror image of this particular edge, right? This is the mirror image of this red one, and the mirror image of this particular red one is this one. Okay, so that's how we can find the graph. Now I'll give you the general graph. So that means for any value of a, how can we find out the graph?
Mom,
Yes.
I didn't understand that 1 by 2 power x stuff, Mom.
Yeah. Okay. So okay. So here, see, if you place mirror over this green line, suppose you have a two-sided mirror and you placed over here, then the mirror image of this red edge will be this blue edge, correct? And similarly, the mirror image of this particular red edge is this upper one, blue edge. Okay, that's how we are getting the graph. Is that okay now? Think like you have put a two-sided mirror, okay?
Yes, Mom, got it.
Okay. So in general, what happens? So in general, if the value of a is between 0 to 1, the graph of log look like this one. Okay, and it will intersect the x-axis at the value 1, because we know that log 1 is equals to 0. Okay, and if the value of a is strictly greater than 1, then the graph of a, log base a, will look like this. Same x-intercept 1, 0. This is log base e of x. And this is also log base e of x. Okay, now by the graph we can judge the properties. So first thing is, in this case, it's a decreasing function, right? Because it is decreasing as the value of x are increasing, and this one, it is an increasing function. Okay, so that means log base a of x is decreasing if the value of a is between 0 to 1, and log base a of x is increasing if the value of a is strictly greater than 1. Okay, so this is the first property. The second property is in behavior. So now you guys can tell me. So limit x goes to infinity, this log base a of x, what will be this in the first case? As x goes to infinity, where this log is going?
Infinity.
Minus infinity, na? Because values are decreasing over here. So minus infinity. Is that okay? Now here we know that we cannot take negative values as our input because we have restricted the domain of log to be strictly 0 to infinity. Okay, so this thing you have to remember, that the domain of log function is between 0 to infinity. Okay, so now we know that we can't take the negative value, so it's not a point to check the limit x going to minus infinity. But we can yeah.
You've written limit extension to be log base a power x equal to minus infinity.
Yeah, in this first case.
Oh, okay.
Yeah, in the first case. In the second case, obviously, it goes to infinity. Right? So what is log limit x going to 0? Log base a of x. So remember here we are talking about the first case when the value of a is between 0 to 1. Okay. So as x goes to 0, you can check here that the log is going to infinity.
Positive.
Right. So here this value is infinity. Now same thing we can ask about the second part, log base a of x. So here this is infinity because as x goes to infinity, this log is growing, so it goes to infinity. And limit x goes to 0, log base a of x. Now this is minus infinity, right? Okay, so these are the end behavior of log function. And obviously log function is 1, 1 and on 2 with the specified domain and codomain. Okay, domain is open interval 0 to infinity and codomain is real number. Fine. Is there any doubt in log? How we are defining? So this is the definition of log. Okay, don't assume it as a property. It's a basic definition. That's how we are defining the log, creating the log. Okay. Now we have other several some. Yes, Shravan. Okay, so now we have some properties of log, that log base a of those properties you guys can go and check. Log base a m plus log base a n, this is equals to log base a of mn, right? These properties you guys can go and check. These are just properties and you have to remember. Okay, now the type of question here they can ask about is finding some values. Okay, so those questions maybe we can discuss later. Currently I am not remembering any that question. So no, actually I do. I'm not remembering one question about this one. But you have to remember these some properties, right? So here for plus we have this property. For minus, we know that log base a minus log base a of n. This is equal to log base a of m by n. And we have one more property which can change the base. So this is log base a of x. This is equal to log base b of x upon log base a of b. Or b of a. So I think this is b of a.
I mean,
Yeah.
log a of base b, yeah.
This one. So these three properties are actually important. So you can use these three properties to solve questions from log. Okay. Theoretical question could be what are the properties of log, and some computational question can be based on this one, or there is one more method that is known to be converting into polynomial. So actually I'll just briefly give you the idea. So what happened? There will be some expression, some equation will be there in terms of log or in terms of exponential function, and there is some constant and you want to find out the constant of that m. There will be some constant. So suppose m is the constant involving in the expression. Okay, I don't have a specific example for this process, but I'll just want to give you the basic idea what you need to do. So suppose such type of question is there, then what you have to do, you have to observe the common term. Common term could be log 2, log base 2, log base 2 of x. Then what you have to do, you have to take t to be equal to that particular common term and replace it with in this equation, and then you can convert it into polynomial, and then you can solve this polynomial and get back your solutions. Okay, so this is known to be conversion in polynomial. So observe the common term in the expression, replace that term with some constant t or x, get a polynomial, solve that polynomial, and then get back the value of constant. Okay, so this is the method is known to be conversion of polynomial. So this method is useful to solve some these type of question where you need to find a constant. Okay, such type of question you may have find out in your practice assignment or activities. Okay, so that's all about log function. Any doubt in log functions? Anything which is not clear? Okay.
And the third property, could you please explain?
Yeah, so actually what happened, if you want to change the base, this is the property, that log base e of x, this is equal to log base b of x upon log base b of x. So you can change the base of any log function using this property. That's why we in general talk about only two bases. One is the natural logarithm, log base e. This is also written as ln, or another one is log base 10, which is sometimes written as only log. Okay, so that means you can change the base of log using this property. You can prove this property by some steps. It's not that difficult, but the main thing is you can change the base of log with some another base b. Okay, that's the important. You can prove it. There is a proof given. Sorry, what?
Can you illustrate with an example, please?
With an example, actually I don't have example for log, but you can change anyway. So suppose I have this 4 and here I have some value of 8. So suppose I want to find this one. What I'll do, I'll say that log base 4 of 8 is same as log base 2 of 8 because 2 is easier to handle, right? Upon log base 2 of 8. Right? But what is this log base 2 of 8? Log base 2 of 8 is log base 2 into 2 cube, and upon this is log base 2, 2 to the power 4. Right? One more property we have in terms of log, that power property, that this power will come out.
2 power 2, madam.
Yeah, thank you. This power will come, jump ahead. Okay, so this is same as 3 log base 2, and this is 2 and log base 2. So you can cancel it out, and the answer will be 3 by 2. So you can use to solve such type of thing. Okay. This could be an example.
In the calculator nowadays, in the exam, our TCS and calculator, base X, base Y also is there, madam.
Yeah, base Y is also there. So
base
these,
Y X. Directly we can feed in the data and you can get 3 by 2.
Yeah, that's correct.
If it is a numerical problem.
But I don't remember the example for this process, but you can find some example. Okay. So properties you can use. Okay, so that's all about log function. Now the next topic is composition of functions. Okay, so what we can do, we can apply a function over a function. So that means first I have something, I have one x, right? Over this x, I'll apply a function f, get an output f of x. And over this f of x, I want to apply another function g and get an output g of f of x. Okay, so this resulting function is known to be composition of g composition f. Okay, so first we are applying f and then we are applying g. So what is g composition of f of x? It's nothing but the image of g applied on f of x. So first you have x, you will apply f on that, get f of x, and then apply g on that and get g of f of x. Okay, similarly we can do in the reverse order also. So for example, you have x, then you want to apply g and then want to apply f. So this is known to be f composition of g. Okay, so f composition g of x is f of g of x. Okay, so this is known to be composition of functions. So you can use more than two functions also. There could be several functions and you want to find out composition of several functions too. Okay, g of f of x or f of g of x or anything. Now, in this particular topic, the main question is how can we find out the domain of f composite g or g composite f. Okay, so now for finding domain of f composite g, first we understand what is the meaning of domain of a function. Finding domain of a function. Okay, for finding domain of function means you have to find all those values, find all those values of x, for which the expression f of x makes sense, or this is well defined. So what is the meaning of well defined? So well defined means first thing, it should be a real number, and the second thing is it should not be equal to plus or minus infinity. Okay, so this is the meaning of well defined. So what we want to, so when someone asks you that find the domain of that particular function f, it means that they want you to find all those real numbers for which the value f of x is a real number. It is well defined. So well defined means either it could be a real number or it is not equal to plus or minus infinity. Okay, so those set of values is the domain of that particular function. So if you want to find out the domain of f composite g of x, then what you need to find out? Okay, so if you want to find domain of f composite g of x, so it means what we want to find? We want to find all those x for which this quantity f of g of x is well defined, right? But here we have two functions involved, f and g. So what is the meaning of f of g of x is well defined means? First thing is g of x should be well defined, and the second thing is f over this g should be well defined. Okay, so what we can do, we can decompose this problem finding the domain of f composite g into 3 steps. First we will find out the domain of f, then we will find out the domain of g, and then we will remove some point from domain of g for which this particular quantity f of g of x is not well defined. Okay, so these are the steps for finding domain of f composition g. Steps for finding domain of f composition g. Okay, so first step is find the domain of g. Second step is find the domain of f. This is domain of g, domain of f. And then third thing, you have to see what we need. This f should be defined over the value g of x. Okay, so that means this we need g of x should be belong to g of x should be a member of domain of f, right? Because domain is a set of all those points where the function is well defined. So if g of x does not belong to domain of f, then you cannot talk about f of g of x, right? So what we'll do in the next step, we will remove all those points from domain of g. Again, I'm saying that we'll remove all those points from domain of g, because ultimately in the first step I want g of x should be well defined. So if g of x is not well defined, there is no way, there is no need to talk about f of g of x, right? So what we'll do, we'll remove all those x from domain of g for which if you compute g of x, it's not a part of domain of f. Okay, so you'll remove all those x from domain of g for which if you compute g of x, it's not a part of domain of f. Because if g of x is not a part of domain of x, you cannot talk about f of g of x. Okay, so these are the steps. Ishravan.
The third point.
Yeah. So I'll take one example, and why I'm saying that you have to use the steps, don't go by the expression. So that means don't first find the expression and then compute the domain. First go by these steps only. So you can take one simple example. So suppose I have example of, suppose your function f of x is 1 by x and the function g of x is 1 by x minus 3. Okay, so here what will be, so I want to find out the domain of f composition of g. So first step is what will be the domain of f? What will be the domain of f in this case?
One
All
it
real
cannot have
numbers
zero.
except
Except zero.
Right. All
all
real number
next
minus
zero.
0.
Except
Zero.
zero.
Right. What is the domain of g?
All real numbers except 3.
Right. All real number except the 3. Right. Now I want to find out domain of f composition g. So the next step says, this is our second step. Next step says remove. So remove those values of x. So remove those values of x from domain of g for which g of x is not a part of domain of f. Okay, so let's try to understand this step, that we have to remove all those x from domain of g for which g of x is not a part of domain of f. So now what is there which is not a part of domain of f? Only 0 is there, which is creating a problem. So what I'll do, I'll first find that x for which this g of x is becoming 0. Okay, so that means I want to find out that x for which 1 by x minus 3 is becoming 0. But there is no such x, right? So in this case, there is no such x which can make g of x to be equal to 0. So that means here this third step does not apply. So here, which means there is no x, there is no such x for which g of x is not a part of domain of f. What I can say that okay, then domain of f composite g is same as domain of g. We don't have to remove anything. Okay, so and what is domain of g? Domain of g is real number minus 3. Okay, so here in this case, domain of f composite g is nothing but real number minus 3. So suppose if you find such an x for which domain of g does not belongs to domain of f, you have to remove that f from the domain of g, and whatever left is there from domain of g, that is your domain of f composition of g. Okay, so from using these steps, we are getting that domain of f composition g is real number minus 3.
Madam,
But for example, yes,
domain of FOG, first you have to find out the function FOG, no, madam.
No, that's not the thing. That's the issue here. So if you find out f composition g of x, then what is this? This is nothing but f of 1 by x minus 3, right? And this is 1 by x minus 3, which is equal to x minus 3. So you'll say that if you go by the expression, and then this is just a real, this is just a straight line, right?
No, what
So
I
domain
meant
of straight
is,
line is real number.
yeah, correct, madam. In this
Yeah.
case, the domains are same, but sometimes you may get as 1 by x minus 4 as domain of FOG. So at that time, even domain of FOG will become r minus 3 comma 4.
Yeah. So
So
that's why I'm saying if you go by the expression, you will get different answer. And this is wrong. Why this is wrong? Because we are applying functions over a chain. First, I want to find an output, and then I want to find another output. So here, if you think that the f composition g is x minus 3, and then you will compute domain, then you will reach at the wrong answer. It is possible that you will include some extra point on which our f composition g, this process is not well defined. Okay, so it's a process. On a function, you are applying another function. So this chain should be valid, right? So that's why don't go by the expression. Don't find the expression and then compute the domain. This is not a correct way.
madam, but ultimately we have to find the expression, no, madam.
Ultimately, but if you want to find domain, you don't need to find an expression. Yeah, ultimately we need to find some x for which this is not a part. So yes, but for finding domain, don't look the domain of the expression. That's why what I want to say.
Madam, what my point is, we get after following all these things, you found out step 1, step 2, step 3. After that, you find the FOG, the function, and the function coming as 1 by x minus 4.
No. Why 1 by x minus 4?
No. Some function, some other f and some other g.
Yeah.
So
Okay.
I get 1 by x minus 4. Now by FOG and DG, it cannot be r minus 3. No, it will be r minus 3 comma 4.
No. Then that function will take care over that 4 in this particular expression. So for that function, domain of g and domain of f will differ, na? So we have to use another things. So that
Okay,
4 will be taken care in this particular thing, in this process.
Okay, no issues. But for my point is, as per in the lecture, the professor has taken one example to show, no, in that domain of f and domain of g were also calculated. After that, the function f of FOG was calculated. Based on all the three, the final domain has been arrived, which will be different if we don't find out the function FOG. Here you stopped with the green chalk. You have stopped without finding out what is the function FOG itself, and you are directly telling that domain of FOG equal to domain of G. But you have never found out what is FOG at all before coming to a conclusion that this is equal.
Yeah.
You got my point, ma'am?
Yeah, I got your point.
So You before
Okay.
finalizing the domain of FOG, function of FOG has to be found out. No,
No, I don't think it's needed. Let me see.
madam. Sure,
I
madam.
yeah, I'll
Without knowing,
check.
function can be any. You can get the final function as anything. There may be some points which were not in F and G can
Hmm.
also be not a part of the domain of FOG.
I'm getting your point, but I think this process will take care of that point. Let me check that example.
Yeah, I think what
Direct
Sarva
example is the professor example. Direct what professor is talking in the recorded video. That example is what I'm quoting.
Yeah, I think what Sir was talking about is exactly this thing, because here you see what happens when you do this FOG or GOF is that X belongs to the domain of G, and hence GX belongs to the domain of F, and hence FOG
Yeah.
has to be in the domain of this thing, right?
Yeah.
So that's what he was referring to.
And your point is well valid and well taken, because final only FOG you find out and then you decide on the domain. That is wrong. That is wrong. You will not get the correct domain of FOG. But you have to find out the function FOG. In that function, there may be or may not be some points which has to be left out.
Yeah, that's correct. Yeah.
Yes, madam. Please proceed, ma'am.
Yeah, but then this holds only if the previous conditions hold, because if this thing is not this, because see GX FOG is a subset of this GX, right?
Yeah, subset of GX.
Yeah, so this holds only if the entire set holds.
Yeah.
So you cannot directly jump onto computing the FOG, because
Yeah.
that's only a subset. So
Yeah.
you are neglecting the entire universal set.
Yeah, that's correct. So we have to take care of the domain of G first, because we want G of X should be defined and then F of G of X should be defined. So, okay. Okay, so let's see. I'm not able to find that example, but yeah, this is the general method. You can proceed in any way. But the thing is, first F of G of X should be well defined and then F of G of X should be well defined. That's all. Okay.
Ma'am,
Yes, ma'am.
ma'am, if we have to find G of F, then will we substitute Fx is equal to that point which does not lie in domain of G?
Correct. So
Like,
we
will
have
I
to
substitute
change
1
the
by
rule.
x is equal to 3? So I'll get x is equal to 1 by 3. That means domain of G of F will be R real number minus 0, comma 1 by 3.
Yeah, that's correct. So if you
Okay,
compute the domain of G composite F, so in G composite F of X, what will happen? This will be a subset of domain of F. And you need to remove all those points for which F of X is not belonging to domain of G. So that means this F of X should not belong to real number minus 0. Real number minus 3 is there, na? Real number minus 3. So that means this F of X, that means 1 by X is not equal to 3 we want. But if you take X is equals to 1 by 3, you'll get 3 back. So that means you have to remove this point 2 from the domain of F. Right? So here in this case, domain of G composite of F will become real number minus 0, comma 1 by 3. So you have to remove 2 points here, not only single point. And in this case also, if you compute the expression, you will get G composite F of X. This is equal to 1 upon X minus 3. Right? Yeah, in place of X, we have to replace F of X. So 1 by X minus 3 will change into 1 upon X minus 3. So this is 1 minus 3X.
Madam.
Okay. Yes.
The example professor has taken is F of X equal to 2 upon X minus 1.
F of X is equals to 2 upon X minus 1.
And G of X is equal to 3 by X.
3 by X. And what is the composition order? G composite F or F composition G?
It's a F composite G.
FOG is finding, madam, and the domain of FOG.
Okay. So here also the domain of F is simple, right? Real number minus 1. And domain of G is real number minus 0. Right? So now if you want to find out domain of F composite G, this will be a subset of domain of G, and you have to remove all those
Saran
points
and
for
Sharan,
which,
please mute yourself.
yeah, please mute yourself. And you have to remove all those points which for which f of x is not a part of domain of G. Okay, so what is the point which is left in domain of G is 0. So I want, so first what I'll do, I'll find that x for which f of x is becoming 0. Right, so that is 2 upon x minus 1 is equals to 0. And again, here there is no point because 2 is not equal to 0 I want, which is not true, right? So here there is no x, that means we don't have to remove anything. So here the domain of f composite G of x will become same as domain of G, which is real number minus 0. Okay, now let's go to expression. What is the expression I'll get? I'll get that f composite G, right? So f of G of x, which is 2 by x, right? 3 by x is there. And this is equal to f of 3 by x is equal to 2 by 3 by x minus 1. 2 by 3 by x minus 1. So this is equal to 2x upon 3 minus x, right? So here x, by the expression, if you think, it says that x should not be equal to 3, right? And by the definition, I am thinking it should not be equal to x is equals to 0. Is that the point, Naren, you want to say? That we also have to remove 3.
Correct, you got the point now. Once you stop it, you cannot say FOG, D of FOG equal to D of G, which is equal to R minus 0. This cannot be the final answer.
Okay.
So you
So
have to find out
you
FOG.
have to remove
Now
x
you
is
have to
equals
remove
to
the 3
3.
also from the domain of FOG, no?
Yeah, because it is possible to get g of x is equals to 3. Is it possible? Yes. X is equals to 1 if you put. Then you will get gx is equals to 3.
Yeah.
And if you put it back, 3 minus 1 or 2 minus 1. Okay.
No,
Ma'am,
for
in
the
that
function
case,
FOG, for the function FOG,
Ma'am,
at
it should
G is not defined, no. It should remove or should not be removed. Madam, we should remove, isn't it, ma'am?
But I think g of 3 is defined and f of g of 3 is what? G of 3.
ma'am, it should be g of x is equal to 0. If we go stepwise.
But we are
Yeah.
finding f composite g, na?
So in f composite G, we check a function of G which does not contain the point of f.
F of yeah. Thank you.
So
This
this should
one
be
I was
G.
thinking. Right. I got confused. So see, here what we are doing, we want f of g of x should be well defined. So that means we are finding those values of g of x which are not part of domain of f. Here I did the reversal. Thank you. Yeah, so this is our point. So that means I have written down the wrong step. The second step is wrong. I want to find those g of x because see, we want to find f of g of x, right? So we have to take care of g of x first and then f of g of x. So those points of g of x which are not in domain of f. So when this 3 by x will become 1. So this means x is equals to 3. Now we have to remove x is equals to 3 from domain. Yeah. So by the steps only we are getting the same points. So that's why I was saying that these steps will take care of each and every point. So here initially, okay, I'll repeat what happened. So initially we have two function f of x is 2 upon x minus 1, g of x is 3 upon x. We want to find out domain of f composition g of x. So that means this thing f of g of x should be well defined. So first thing is g of x should be well defined. That means we have to take those points from g of domain of g only. But then f of g of x should be well defined. That means this g of x should belong to domain of f. So what we'll do, we'll find those points of those points x for which this g of x is not a part of domain of f. And in domain of f, there is only one value, which is 1. So what I'll do, I'll find out those values for which g of x is becoming 1. Okay, so this g of x is equal to 1 means 3 by x is equals to 1. This means x is equals to 3. So we have to remove this 3 from domain of g. So that means from domain of g, we have to remove 2 points. One is 0, another one is 3. So this will be the domain of f composition g of x. Okay, so thank you. That's the point we are missing. That's why I say why this process is not getting. Okay, so ultimately, if you find the expression or not, you will get the correct answer by the steps only. Okay, is that okay, Naren?
Yes, madam. Yes, madam.
Yeah, it will take, the steps will take care of the well-definedness.
Okay.
Okay.
Okay. Got it.
But yeah, you should take care of this second step, that which you have to
Properly.
remove which points. Okay.
Properly, we have to take care.
Yeah.
Okay.
Okay. This is the important question on the important and little bit tough question from composition of function topic. Okay. Other questions, could we find the expression and all those things? Those things are easy for you guys, right? Any other thing? I don't think there is from composition of function. Okay. Finally, is there any doubt so far? Yes, Levan.
Can you do one more example for this question?
Another example I don't. Okay, one thing we can do with roots. Okay. So suppose f of x is root of x minus 1 and g of x is 1 upon x. Okay, suppose take 1 upon x. Okay. In this case, I want to find out domain of f composition of g and domain of g composition of f. Let's find out both. Okay. So first thing is domain of f composition of g. Okay. So this will be the subset of domain of g. What is the domain of g? So domain of g is real number minus 0. And domain of f is what? So here we have under the root function, and we know that under the root function won't define for negative values. So here in place of x, if you take any value which is less than 1, you will get negative. So that means x should be strictly greater than or equal to 1. 0 is all, x is equals to 1 is also allowed. Okay, so these are the two domains we have. So domain of f composite g will be a subset of domain of g. That means real number minus 0. Now what we have to do, we have to remove those g of x which are not part of domain of f. Okay, so for that, what I'll do, I'll first find those x for which this g of x is I want strictly greater than equal to 1. Okay, so first I'll find out those for which this is strictly less than 1, and then we can go on, right? So g of x is strictly less than 1 means x 1 upon x is strictly less than 1. So this means that x should be strictly greater than 1, right? 1 should be strictly less than x, right? That means x should be strictly greater than 1. So if you take any x which is strictly greater than 1, then this g of x will be strictly less than 1. Okay, so this is something reverse. So what does it mean? It means that if x is strictly greater than 1, then g of x is strictly less than 1. Okay, because kind of obvious, x is strictly greater than 1 will imply 1 by x is strictly less than 1. But I want those points, those x for which g of x is strictly greater than or equal to 1, not strictly less than 1. So what I'll do, so it means that, so this means if x is strictly less than 1, then g of x is strictly greater than 1. And if x is equals to 1, then g of x is equal to 1. So that means these all x are allowed. If you take any x which is strictly less than 1, then the value of g of x will become strictly greater than 1. That means it's allowed in the domain of f. Okay, because domain of f is all real number for which the values is strictly greater than equal to 1. So that means we have to take those x which are strictly less than 1 plus x belongs to domain of g also. So what is domain of g? Domain of g is real number minus 0. And we have to take off strictly less than 1 2. So that means here we will get domain of f composition of g as nothing but all those values of x. So that means x belongs to minus infinity to 0, because we have to remove 0, right? Union with 0 to 1. 1 could be close, right? Because 1 less than 1 is also allowed. Okay, so this will be the domain of f composition of g. I'll repeat once again. So now we don't find out the domain of g composition. I think this example is sufficient. So see, initially domain of g is real number minus 0 because the expression is 1 by x. So at 0, it's not well defined. F of x is under the root of x minus 1. So domain of f is x greater than equal to 1 because we want a positive quantity under the root, right? Now the domain of f composite g is a subset of domain of g. This much we know. And the second step says we have to remove all those points from domain of f for which g of x is not, sorry, we have to remove all those points from domain of G, for which
Yeah, just give me 1 second, I'll be back.
Can you please someone tell me, is that video playlists are enough? Naren?
What, sir?
That video playlist enough for the exam?
No, not.
Video playlist they have given, no, in website, in YouTube.
No, that is for this particular session. What she is taking, that is the link.
No, I'm asking for exam, not for this particular session.
No, I don't know how to answer this question. See,
Uh,
for exam point of view, I am not able to answer that question. To pass the exam, that should be enough.
Okay. What I am asking is, if we go through all those video lectures, will we be able
You can be
to
able to get a good marks. Yeah.
Okay. That's what I.
Okay.
Okay. Thank you.
Hello, am I audible?
Yes, ma'am.
Yes, ma'am.
Okay, so let's recall. So we have taken the function f of x is equals to under the root of x minus 1, and g of x is equals to 1 by x. So here what has happened, domain of G is real number minus 0, and domain of f is all those real number which x is strictly greater than or equal to 1, right? So you can say that as an interval, if you want to say closed interval of 1 to infinity, right? These are both things are same. Now we want to find out domain of f composition of G. So we know that this will be a subset of domain of G, and we have to remove those x for which g of x is not a part of domain of f. Okay, so what is the not a part of domain of f? That all numbers from minus infinity to 1. Okay, so that means g of x should be greater than or equal to 1. This is what we want. Okay, this is what we want. So if g of x is greater than or equal to 1, it simply says 1 by x should be greater than or equal to 1, and it simply says x should be greater than or equal to 1. Okay, so sorry, less than
equal to 1.
Less than equal to. Okay, so that means this condition we got, that we want first of all x should belongs to domain of G, and x should be greater than or equal to 1. So that means x should belongs to real number minus 0, and x should be greater than or equal to 1. So this thing we can write in terms of intervals. This is less than 1. This is less than 1. No? This thing less than 1. So this thing we can write as an interval to be minus infinity to 1 closed, and this thing also we can write as an interval to be minus infinity to 0 open union with 0 to infinity. And what I want the combination of these two conditions. That means I want the intersection of these three intervals. So you can find out the intersection will be minus infinity to 0 and then union with open 0 to 1. Okay, now this will be a required domain of f compositions.
Ma'am, but I have a doubt.
Yeah.
Ma'am, for example, if I take x is equal to minus 1 in f composition G, then I will get g of x to be minus something, ma'am.
X to be what?
Minus 1.
Minus 1. Yeah, then g of x
G of
will
x should be minus 1.
minus 1. Okay, this is
Then
less.
if I put that over here, it will become minus 2 root.
Yeah, that's correct. Minus 2 is not defined.
So it would be only 0 to 1 now.
Oh, sorry, I have to take the intersection now. Yes, yes, you are correct. Yeah, so we have done so far is okay, but this intersection part I have missed. So ultimately we have to take the end. So that means x should belongs to domain of G and x should be less than or equal to 1. So that means union of these two with intersection of this one. So if you do the intersection, this is minus infinity to 0, union with 0 to infinity, intersection with minus infinity to 1, right? So interval wise, this is something like that. This is minus infinity to close 1, and then we have 0 somewhere here, and we have to take the intersection. Okay, still it doesn't make sense. So ultimately x will be between only 0 to 1.
And these are the x's that you have to remove out, right?
Ma'am, the point x less than or equal to 1, I guess it should be excluded from domain of G, right?
Yeah, it should be
Yeah. It should be excluded from domain of G, not included. So initially I have written correct. So I want x to be greater than 1, not less than 1. Right? This was correct initially, right? So ultimately we want this.
It
G
should
of
be
x.
x only, x greater than 1 only should be taken, right?
Yeah,
Because
greater than 1 only should be taken.
not
So we
equal
have
to
to
11,
remove
greater
this
than
one.
equal to. But not greater than equal to, I think. You should take
Equal to
only.
will work. So that means open interval 1 to what you can say infinity.
I think it's closed interval, right?
Yeah, close interval 1 to infinity. And we have to, okay, so x should be greater than equal to 1. Any value greater than 1 you can take. If you take lesser value, the 1 by x will also be less. Yeah, correct. So that means ultimately is close interval 1 to infinity. This will be the domain.
1, we will include or exclude 1?
No, we'll include 1 because 1 minus 1 will become 0. So that will is okay. Under the root of 0 is 0. Okay. So we'll check this example one more, but I think this is correct answer now. Open interval, close interval 1 to infinity. Because if you take any lesser value here, that's also work here. Because see, if you take 1 by 2, that 1 by 1 by 2 is 2, then 2 minus 1 is 1. So that's also work. So only thing we have to remove is, yes.
Domain of F composition G would be 0 to 1 closed.
Then open interval 0 to 1, 0 to infinity. Na? Wait a minute.
Then that would be problematic because see, if you do FOG,
Hmm.
it turns out to be root over of 1 by x minus 1. And
Yeah,
if you,
1 by x minus 1.
yeah, so here x, if you take 1 minus this, entire thing will be root over 1 minus x by x. So if x is greater than 1, anything greater than 1 should be giving you a complex number.
Yeah, that's correct. So ultimately, x should not be equal to 0. And if you find out anything which is greater than 1 here, you will get the complex number. So that means here, this x should be less than 1. So x is not equal to 0 and x should be less than 1. These are the only two things we have.
Yes.
So,
Ma'am, less than or equal to 1?
I mean, here your x should be...
Equal, it can be equal to 1. No?
Yeah, good. Equal to 1, we don't have to remove, right?
Yeah, ma'am. So it can be less than or equal to 1.
Less than or equal to 1. Right.
Yeah.
The constant would be
No,
x greater than 0, x less than 1. Less than or equal to 1, ma'am.
Yeah, so these are the points we need to remove, right? But not equal to. We can take x equal to 1. See, at x is equals to 1, this will become 0. Right? So x is equals to 1 will obviously there. Now the only thing is...
Ma'am, no, ma'am. These are the points actually there. All other have to be removed, ma'am.
No. If you take x is less than 1, then this 1 by x will be greater than... Yeah, these are the points we have to take. Just 1 second, I'll be back attending this.
X should be between 0 and 1 only, you know.
Okay, so let's check this once again. So see, this is our function f composition of g. So initially, obviously x should not be equal to 0. And the next thing is we want this bracket to be strictly greater than 0, right? That is 1 by x minus 1 should be strictly greater than 0. That means 1 by x should be strictly greater than 1, and that means x should be strictly less than 1. Okay, if I want this to be strictly greater than 0. So that means x, the values of x should be strictly less than 1. That's the only thing we have, plus with the value that x is not equal to 0. Right? So both things we have to combinedly write. And the thing is, we can take x to be less than or equal to 1. Because if you take x is equals to 1, you will get the composition, f composition g of x to be equal to 0, which is well defined. Right? So here the answer will be x is less than or equal to 1 plus the condition 0, plus the condition x should not be equal to 0. Right? So what will be the interval we can write? So here x is less than equal to 1 means infinity minus infinity to 1 close, and plus that x is not equal to 0. Right? So you can write minus infinity to 0 open union with open 0 to close 1. Now this will be the composition f composition. Now is that okay? Clear? And right? I think
No,
Yes, ma'am.
X as
Yes,
minus
ma'am.
2.
Sorry, what?
If you put x as minus 2.
Minus 2, then it is creating a problem, no?
Yeah, it should be between 0 and 1 only.
Only 0 and 1.
Yeah.
But if we go with this condition that 1 by x minus 1 is strictly greater than 1, 1 by x is strictly greater than 1, x is greater than equal to 1. Okay, so if you take negative values, then minus and minus will ultimately become minus, right? So that means we have to remove the negative numbers too. So it's
And
only
if we go
between
with steps, then also negative cannot be included.
Sorry, what?
Ma'am, if we go with steps like x is less than or equal to 1, we have to remove that, na? So we
Yeah.
cannot substitute negative values.
Negative values also because of the domain of f. Right? So I think ultimately we'll reach to this point if you go via the steps also, open interval 0 to close 1. So see here also, if you go by the expression, then we are getting only one thing, which is x is less than equal to 1. But if you think, then we have to only take care of the numbers between 0 to 1. Then it will be okay, right? Is that fine now? Open interval 0 to 1?
Yes, ma'am.
Yes,
No,
ma'am.
ma'am.
Okay, so what we can do? And we'll recheck the steps. Okay, so domain of G is real number minus 0. Domain of f is all x which are greater than or equal to 1. The domain of f composition G will be the subset of domain of G. Now what we have to do, we have to remove all those x for which domain of G is not a part of domain of f. So what is there which is not a part? So not a part means G of x. Okay, I'll remove this whole part. Okay, so what we have to do, we have to remove those x for which g of x is not a part of domain of f. So that means 1 by x, so that means those x for which 1 by x is, so what are the part of domain of f? Part of domain of f is greater than or equal to 1. So not part of domain of f means less than 1. So that means we have to remove all those x which are strictly greater than 1. Okay, this part we have to remove. Okay, greater than or equal to 1 we can take actually, because at 1 it won't create a problem. Because here we are taking greater than or equal to 1. So negation of greater than equal to will be strictly less than. Okay, so this thing we have to remove. So what I have to do, I have to remove 1 is strictly less than x, this part. And that means I have to remove all those x which are strictly greater than 1 from domain of G. Okay, so what is domain of G? Domain of G is real number minus 0. so the domain of G is real number minus 0. From this one, we have to remove all those x which are strictly greater than 1. Okay, so ultimately, we are not ultimately we are getting negative numbers if we go by the steps.
Ma'am, but if we take negative numbers, we're gonna get.
We are getting negative numbers. Yeah, this is clear from the portion. Is there anything I have missing? Okay, so I have found the wrong domain of f.
Actually, we can assume that f of x cannot be negative one. So we have to take that g of x cannot be negative. So the domain of, range of g of x would be 1 to 0 to infinity.
Yeah, correct. So that thing we can do, that we are not taking the negative numbers in domain of f and domain, but domain of g could be negative, but that's also creating a problem. Okay, sorry. So see here, we are removing all those x which are greater than 1. No, we are not removing negative numbers here. I don't know what is happening over here, so we'll figure it out once. I'll check once again. Okay, so let's go to the other topics and then we'll get back to this question. Still, I am confused that what is happening there. So I'll get back to you. Okay. Yeah, so what are the next topic we have? After composition, we go to sequences. Okay, so let's talk about sequences. So what are sequences? The definition of sequences is all those functions from natural number to any set. Here you can use as any set. Any set could be real number, natural numbers, complex number, or any set you can take. So such type of functions are known to be sequences. Okay, so this is the definition of sequence, that a sequence is a function from natural number set to any set. Now there are several representation of sequences. One thing is you can just as like functions, we have given some expression, you can give some expression to this function also. So you can say that f of n, we'll use small n whenever we want to represent a natural number. Okay, so f of n is equals to 1 by n. So now this will represent the sequence. So now another expression for sequence is just listing the elements. For example, if I give you a sequence with f of n is equals to 1 by n, you can list out the elements in an order. That the first element will be, if you start with 1, again I'm starting with 1. Okay, so here that thing that natural number 0 includes in the natural number will create a problem. That's why let's take n plus 1. N belongs to a natural number. Okay, so here if you list out the elements will be 1, 1 by 2, 1 by 3, 1 by 4, and so on. Right? So the first way of expressing a sequence is by the closed form, f of n is equals to 1 by n. Another way is just listing out the elements, or the third way, in place of f of n, you can write a subscript n. Right? So this is known to be the nth term of the sequence. So you can also give the expression for nth term of the sequence and define your sequence, that an is nothing but 1 upon n plus 1. And one more way to represent this sequence is the recursion form. Recursion form means you will give relation between the next term and the previous term. For example, I'll say that a1 is equals to, a0 is equals to 2, and I'll say that an plus 1 is nothing but 2 multiplied by an. Right? So using these two terms, these two things also, we can define a sequence. The sequence will be a0 is equals to 2, a1 will be 2 into a0, which is 2 square, a2 will be 2 into a1, which is equal to 2 cube, and so on. So this type of form is known to be the recursion form of the sequences. Okay.
Ma'am, can you repeat?
Yeah. So we have a topic sequence. So what is a sequence? Sequence is nothing but any function whose domain is the set of natural number. This is the definition of sequence, that any function with the domain of natural number is known to be a sequence. Now there are several ways to define a sequence. One is just by giving the expression of a function. We know that a sequence is a function, so we can say that f of n is equals to 1 by n. This will represent a sequence. Okay, so this is one type of representation of sequence. How to denote a sequence like that? Another one is we can list out the elements 1, 1 by 2, 1 by 3, 1 by 4, and so on, and say that this is a sequence. Another one is giving the expression for the nth term. Nth term is what? What is the nth term in this sequence? This is your first term, second term, third term, fourth term, and so on. So if you give the expression for generating the term, that's also tell us what is the sequences. So you can say that the nth term is nothing but 1 by n plus 1. And the last one is the recursion form, that given the relation between en and en plus 1. Okay. Yes, any doubt?
Ma'am, just one thing. So I have found a couple of things from in the last question.
Yeah.
So in the last question, if you see that g of the FO, I mean, we are computing this g of x. So all those x's that for which, I mean, all those x's in excluded for which gx belongs to the domain of f, right?
Yeah.
So our condition should be 1 over x should not belong to from 0 to should not belong to minus infinity to 0.
Minus infinity to 0. Why is that?
Yes, because the domain of g is from minus infinity to 0, right?
No. Domain of g is real number minus 0 only. G is 1 by x, no?
Okay.
Yeah.
Okay.
Yeah, that's the thing. So I have to check that example once again. I'll check it and post it in the chat, or I'll post the PDF over the calendar. Okay. I'll solve it in detail and then I'll post.
We have enough time, madam. Still, the 13th only is end term, so we can proceed.
Yeah, that's correct. So I'll think about that example once again. Okay. So in sequences, we have to find out the limit of sequence, limit of a. So what is this limit of a means? You need to answer this question that as n goes to infinity, where does the terms of sequences are going? Okay, this is the question we need to answer. As n goes to infinity, where does an goes? And if you answer that question, that's your limit of sequence. So the one thing is, the limit of sequence we are defining for, we can find out the limit of sequence using some formulas also. So some simple sequences we have. So what will be the limit of 1 by n, limit of n goes to infinity of 1 by n? What will be this limit?
0.
0.
Because as n goes to infinity, 1 by n goes to
0.
0.
Yeah, sorry for the interruption. Actually, I was talking about this thing only. That 1 over x does not belong to minus infinity to 0, right? Because the domain of f is from minus infinity to 0.
No, actually, domain of f.
Yeah.
See, domain of g is real number minus 0.
Yes.
And domain of f is all those x which are greater than or equal to 1.
Yeah, I mean, these are to be excluded. I'm talking about those points which are to be excluded.
Yeah. So you are saying that these points should be excluded. Yeah, that's correct. Those points which are excluded, that's okay. We have to exclude all those x which are strictly greater than 1. Correct. This
Yes,
we need to exclude. But the thing is, why we need to exclude the negative numbers too?
Yes, because if you check with the FOGX, then you get root over of 1 by x minus 1, right?
Yeah, by the expression it's clear, but by the our this 3 steps, why it's there? That's the question.
Okay, so if you check with your algorithm, so you go for the third step, right? So where you say that remove all those x from domain of G for which Gx is
not a domain of
F. Yeah. So domain of F here, which would be excluded, would be from minus infinity to 0. Or 1 over x.
I mean 1 by x, I want 1, what are those values for x for which 1 by x is less than 1 is all x greater than 1. So we have to remove all those x which are greater than 1, correct?
Yeah, so what I am doing is that I am removing all the, yes, exactly.
But so, yeah, same thing, but why we need to remove the negative numbers?
Ma'am, it is because f of x should be greater than 0, ma'am.
Yeah, f of x is greater than 0, that's correct. Okay, I'll think about it and let you know.
Let's continue with the topics.
Because we have limit continuity differentiation. We have to go to the last topic. Okay, so here some basic, in sequences you need to find out some basic examples only. So suppose what will be the limit of, we know limit of n goes to infinity 1 by n. What will be the limit of n goes to infinity minus 1 by n? It will be 0, right?
Zero.
1 by n or minus 1 by n. It ultimately approaches to 0. Similarly, you can say what will be the limit of limit n goes to infinity minus 1 to the power n by n. What will be this limit?
0 mark.
0. Right? Because ultimately what is happening, we are oscillating between 0. So one term is here, another one is here, here, and so on. Okay. So in sequences, you need to find out only such simple limits. There is no complicated limit, because in sequences we haven't done some other theorem. So there are some major theorems which are used to solve some complex sequences. But in our course, we will solve only limit of these simple sequences. Okay, I'll give one example. Try to figure out the limits. A to the power 50, 50 a to the power 50 plus 49 a to the power 49 plus and so on plus a plus 1. And here I have 25 a to the power 50 plus 24 a to the power 50 49 plus a to the power 48 plus a to the power 47 plus and so on plus a plus 1. Okay, so suppose this sequence you have, then what will be the limit here?
2.
And something is 2, right? So actually what happened, you can take care of, now this is n, not n, not e. Okay, so what you'll do, you'll take care of largest power of n and then find out the limit. So if you take care of largest power of n, ultimately you will get this form, that you will have 50 here, then plus 49 upon n plus and so on plus 1 by n to the power 49 and plus 1 by n to the power 50. Now in the denominator you will have 25 plus 24 upon n to the power 49, 48. Yeah, 49 and sorry plus n plus and so on, and ultimately you will get all terms which has 1 by n, and these terms will go to 0. So at the end you will just get 50 by 25, which is nothing but 2, right? So the limit of sequence is nothing but 2. So such type of questions only will be there, because in sequences we haven't done much thing. So these rational sequences or under the root and so on, these things will be there. Now, if a recursion relation is there, so suppose you want to find out the limit of some recursion sequence, suppose an plus 1 is equals to under the root of 3 plus an. Right? Suppose such type of limits you want to find out, then what you'll do, you'll just substitute the value of L in place of an and find the value of L. That is, L is equals to under the root of 3 plus L, and then find the value of n and discard something. So this will be the process for recursion. Okay. So these things, I think.
Sorry, I don't understand the recursion part.
Okay, so actually what happens, so in recursion, if you want to find out the, I'll take one precise example. So let's see the example of find the limit of an plus 1 is equals to under the root of 7 plus an. Okay, where what is e naught? E naught is 7, root 7. Okay. So here if you compute the terms, so compute will be a1 will be root of 7 plus root 7, right? a2 will be again root 7 plus root 7 plus root 7, right? Something like that is there. Now here if you want to find out what is the limit n goes to infinity of an, right? Then what you will do, you'll just take say that, okay, let's let limit n goes to infinity of an is L. Then obviously that limit n goes to infinity of an plus 1 is also L, right? Because what is an plus 1? An plus is nothing but a sequence with one lesser term or an extra term, right? So here if you apply limit n goes to infinity, you will get the equation L is equals to under the root of 7 plus L, right? Now what I can do, I can have a polynomial here, L square is equals to 7 plus L. So that means L square minus L minus 7 is equals to
What
0.
is the L?
L is the limit of sequence. Limit of sequences, we are assuming L and then just applying the limit. Okay. Now this is a quadratic.
The sequence is not a limit, no, it is a n plus 1 is root of 7 plus an, right?
Yeah.
Then why do you put a L there?
So see, if you want, so one thing is, it's not clear that how this sequence actually converges. So what happened here, the increment is very small. So that's why this ultimately you will get a limit. Ultimately you'll get so the reason behind that why this particular limit exists is this sequence is some increasing plus bounded type of sequence. Okay, so this is not in our course. So in our course only recursion is there. So if someone asks you about the question in form of recursion, they'll always give you the hint that okay, limit exists and now you have to find out.
Okay.
Yeah, so here they will give you that limit exists, because if it's an NAT question, obviously limit will exist, then only you can write a finite number, right?
Okay.
So in that case, what you have to do, you have to substitute L in terms of in places of ANs, whatever AN plus 1, AN plus 2, AN are there, substitute that, get a polynomial. So here I'll get a polynomial. Now I can find out the root of this polynomial using just our formula. So L could be that minus b plus minus under the root. So minus b will be 1 plus minus under the root of b square minus 4ac. Right? So that formula I'll do. So b square will be 1 minus 4 ac will be 28 plus 28, right? Because minus 7 is there. And upon 2a. So here there are two values of L. L is equals to 1 plus under the root of 29 by 2. And another one is L is equals to 1 minus under the root of 29 by 2. Okay, is that fine so far?
Yes.
Now here you can observe that this quantity is the negative quantity. Right? This is less than 0 because here we have under the root of 19. Under the root of 29. Under the root of 29 is greater than 1. Right? Because it is very much approx to under the root of 25, which is 5. Right? So this is a negative quantity. But here you can observe that all terms, whatever sequential term you are getting, all terms are positive. So that means it is not possible to get a limit as a negative value. So you will discard this choice and you will select this one as your answer. Okay, so this will be your limit. Is that fine?
Yes, ma'am.
Yeah.
So there are a lot of chances this type of question may appear in n term.
Correct. No, that's I can't say.
You tell correct, and then I can't say.
No, I have to remove this part from recording then. Okay. So
Please remove it immediately.
yeah, so these are the things you have to, I mean, this much you should know, that how to tackle the limits of recursion relation if it is given that the limit is exist. Okay. Now we have limit continuity and differentiability part. So I'll leave that for the next session. We'll discuss it in the next session, if that will be fine for you guys.
Yeah, right.
Yeah.
Ma'am, when would be the next session?
It is scheduled in your calendar, I guess. So let me check.
Ma'am, where can we get that calendar?
So I think for that student, they haven't have calendar, but they will inform you by the mail. So the next session is on Saturday. Revision session.
And when we will get our admit cards or hall tickets, whatever?
You will get before your exam. So these things will managed by the support team. They will inform you when you will get your exam, when you will get your admit cards and all.
Ma'am, I haven't get the week 12 contents.
Yeah, there is no week 12 in our course. So only we up to week 11 we have.
But we received the communication on group that there will be week 12.
In maths
We
one, there
are
is no
not receiving any communication from your end. That content also we haven't received any for 1 week also.
Yeah, it's true. For some subject it is there. For some subject it's not there. So
yeah, for maths.
really.
So about the communication, you can mail to support team, right? They will get in touch of you, because these things we can't do anything. Yeah, I can put forward your whatever things you have, whatever difficulties you are facing. That thing I can tell to the support team from my end.
Okay.
Yeah, yes, someone raised their hand now.
Yes, ma'am. Ma'am, I am a direct entry diploma student. For me, the week 5 tutorial is not only tutorials are there, but not the lectures.
Not the live sessions?
Sorry, ma'am. Yes,
Yeah.
in that course playlist, whatever they have provided in the email, or those are not having live sessions, ma'am.
Let me check with them. I'll write it down and inform you in the next session. For
Yeah.
DA student, right?
Yeah, for dad in programming.
Okay, yeah. Yeah, I'll tell these doubts to support team. They will get in touch to you.
Ma'am, regarding the quiz 2,
Yeah, I have told them several times.
answer sheet till now they have not even responded, ma'am. I don't
Yeah,
know.
they haven't responded. Even they haven't responded to me. I have told them several times. Since I'm working from home, so I'm not going to office.
Okay.
Yeah, that's the thing. So I have tell now Vishal sir. So he will go to office and he'll check with them.
Sure, ma'am. Thank you.
Ma'am, for end term, we have to prepare from week 1 to week 11 only.
Yeah, but the weightage will be different. So there will be more questions from week 7 to the last 11, and less weightage from 1 to 10. But we'll tell the exact weightage in the coming revision sessions. Okay.
Okay, ma'am.
Ma'am, this program is for PG and UG, or for both, or only for PG diploma?
Both, I guess. Both.
PG diploma. There is
Only
no PG diploma. No,
It is not for post graduation.
Any new program has started? No.
there is